All right, lesson 3, applications of exponential growth and decay. So we saw one very specific type of lesson last week, which was one very specific type of application, which was our financial math. And we use a different formula for that one. We use a very specific formula that works well in financial math, and that's this guy right here. A is equal to P1 plus I to the power n. And it looks very similar to the formula that we're going to use in this section, the more general formula, which is this guy. Y equals AB to the power x. So A is kind of the same as the P value. This capital A is the same as our Y value. That's kind of our solution, or the amount that you have. B is kind of your growth rate in this case. And in this one, it's the 1 plus I. And we've already talked about how to find that 1 plus I. And x is like n. And the only hard thing to do in the financial formula is to find your adjusted I and your adjusted n based on what the compounding period is. If you can remember that you're really looking for that I star and that n star every single time based on that magic number, then you should be okay with that stuff. Okay, now this lesson I actually think this is one of my favorite lessons. I really like exponential functions. I think they're really not too hard to understand, and the math behind them isn't too bad either. This is just a nice, moderately difficult lesson, and once you get it, and if you come into this with confidence, then you're going to be just fine with it. And there's a lot of different applications, so we're going to be using this for quite a while. Okay, before we actually jump into it, well, let's actually go over this. An exponential function is a function whose equation is in the form, so this is our kind of general form. There's actually another version of this we're going to get halfway through the lesson, and that's the one on your formula sheet. And it just has one extra variable, which we'll get to eventually. It's actually a number underneath the x. Yeah, they actually changed the x to t over p. And we'll get to that halfway through the lesson. But for now, this is what we're looking at. A cannot equal 0. You can't start with an initial population of 0. And B has to be positive. This function doesn't make any sense if B is negative. If it's decreasing, it has to be a fraction. And if it's increasing, it has to be bigger than 1. And that's what we have written right here. So when the growth rate is bigger than 1, if it's like 1.1, that's 10% growth. That's growing. If it's a half, it's actually decaying. It's becoming half of its original value every iteration. So B is really where all the interesting stuff happens, and being able to calculate the B value correctly is the first challenge of this unit. So we're actually going to do a bit of it aside. Sorry, I'm all stuffed up. So for the B values, percent increase, percent decrease. Our B values are always usually with the language of a percent increase or a percent decrease. And percents can be very, very confusing in mathematics. And I've seen a lot of people struggle with interpreting percents for far longer than they should. Once you get it, it's actually not too difficult a concept. The thing that makes it difficult, though, with percents is there's two very different ways of talking about percents. There's percents relative to an original number. So these ones we would call our relative ones. So relative is a percent. You're talking about how much you had originally, and you're talking about just a percent increase or a percent decrease. So if you have any kind of a relative word in the language being used, that means it's going to be a relative use of percent. But there's another way to do it as well, which is the absolute way. So it's very different whether you're going to say there is 200% of the students that there was last year. That's an absolute way of talking. Yeah, that should be our example. Let's say we had 100 students last year. Let's not use 200%. Let's say 50%. So if I was going to use the absolute way of talking about it, we had 100 students in our school last year. This year we have 50% of the amount of students that we had last year. So 50% of the amount that we had last year, that's an absolute way of using percent. that means you have 50% of this amount. So all you have to do is multiply it. In that case, you're going to be multiplying it by 0.5, and you're going to end up with 50 students. So in the new year, you now only have 50 students. Okay, so that's the absolute way of doing it. The relative way of doing it, and this is actually the more common way. People do use both, but we far more often actually are using relative words when we say percents. So what I could have said instead is we have a 50% increase in the number of students, or the amount of students has grown by 50%. So any kind of word that makes you point to the original number means it's going to be a relative one. In that case, we're not going to be multiplying our 100 by 0.5. Now you could, but then you would have to add that back to the original, right? But we'd like to do it in one step, actually. So instead, in this case, we would actually multiply it by 1.5. And that gives us 150 students. So if the amount of students has grown by 50%, or increased by 50%, you're going to multiply by 1.5. Okay, new number. What if we have 90% as many students as last year? Well, that's an absolute way of talking. So you would multiply it by whatever that is as a decimal, which is 0.9. You have 90 students now. If we say you've increased by 90%, that means you would be multiplying by 1.9, which is 190 students. So for all of the relative ones, that always is relative to 1. We always want to take the original number and treat it like a 1, and whatever the percent that we have, we're either going to be increasing above 1 by that amount or decreasing beneath 1 by that amount as well. So let's say if I wanted to get back to the same number using the relative way, I would say it's decreasing by 10%. Or the amount of students in the class has decayed by 10% over the last year, or gone down by 10%. Any of these numbers. And in that case, I'm not multiplying by 0.1. I'm not multiplying by 1.1. If it's decreased by 10%, so it's gone down by 10%, I actually have to start at my original 1. So I'm going to take my 1, and I'm going to subtract 10%. So the number I'm looking for is actually 0.9. So in that case, I would multiply by 0.9, and I would end up with 90 students in the school. So there's a lot of different numbers you could look for when you're talking about percents. In exponential functions, we're always looking for the amount of students still in the school. So we don't care about how many students left the school. We don't care about the 10 students that left. In this case, we don't care about the 90 students that came. We care about how many students are in the school in total. We want to get right to the answer in one step. These are kind of called the one-step answers. One-steppers. So in one step, you always add or subtract the 1 at the very beginning, and then you get right to your answer. There's 190 kids in the school, or you do this times 100 and get to 90 kids in the school. So let's try that a couple more. Let's say the amount of my house went up by 15% last year. What number would you multiply the original 1 by for that? So I'm looking for our blank. What did we use for our blank? Let's say A, because we're going to use that anyway. So we're going to say A times what? Let's say the value of your car, you got in an accident, and now your value of your car has gone down by 25%. And let's say the population of Lethbridge has gone up by 5% last year. So let's find out what each of these multiplication numbers are. These are our B values. We're solving for our B values in each of these cases. And every single one of these was the relative sense. I always talked about it relative to the original number. And this is definitely the far more common when we get to in exponential questions. The other almost never happens, but sometimes in language it happens, and to confuse people. If you're going up by 15%, my house value, you're going to multiply it by 1.15. So 15% above the original 1. And that should get you to your new house value after 1 year. Your car went down by 25%. You take your original value of your car, and you're actually multiplying it by 3/4, by 75. So again, you take the original 1 and you subtract 25% this time. So you multiply it by 75 to find out what the value is remaining. And the population of Lethbridge went up by 5%, so you take your population of Lethbridge and you multiply it by 1.05. Not 1.5, not 0.05, nothing else. It's 5% above the original 1. So be careful with your zeros. Sometimes people mess that up and they put 1.5 for some reason, and that's really going to mess you up. Okay, so that's the first challenge. If you can understand your b-values and how to get to these numbers, then you're going to be well on your way. Then the only challenges are going to be setting up the equation and solving it using logarithms from time to time. Hopefully this makes sense because everything in this chapter relies on that. Okay, now that we've got that out of the way, I should be able to move fairly quickly through this lesson. I have to use my answer key actually to go through this lesson because my printed notes weren't in the right order. They didn't have all of the right questions or anything. But I can do some of the examples with you guys as we go. Actually, let me just check here. Actually, I do have some of the examples. They're just out of order. So I'm going to just read some of these examples and explain them, but I'm going to do examples I wrote them down here, 3, 4, 5, and 6 together because those ones are a bit more challenging. The first ones are actually pretty easy. So let's just start at the very beginning. Example 1, can we come up with an equation and answer some simple questions based on that equation? So in 2012, the university population of a country was 160,000 and was increasing at an annual rate of 4.5%. Now be very careful with what the units are every single time, what the x value, what we're measuring time by. For the first couple examples, there's not going to be any tricks, but eventually there will be. You always have to make sure you're measuring it the right way. Sometimes they'll give you the growth rate in terms of years, but then they'll ask you months in the future, so you have to convert that. There very well could be many questions that are tricky with their units, so always be careful what the units are. So we're doing it every year, annual, of 4.5%, which means that we're going to be multiplying, increasing by 4.5% means multiplying our b-value is 1.045. Should be what we're using for that. Okay, if the function representing the population is of the form, state the values for a and b. So a is the initial value, 160, and b is exactly what we just said, the original 100 plus 4.5, which should give you the decimal 1.045. So if you can find those values, we can set up the equation just fine. Write the equation. So the population is equal to our a value times our b value to the power n, where n is the number of years since 2012. So you have to also be wary where it actually starts. For exponential functions, it is actually kind of fun that you don't always have to start at year like 0 or something like that. You can actually pick any year, and if you know its population for that year, you can pick that and you can call that the beginning. And you can actually solve exponential problems backwards as well. So using the fact that it's going up by 4.5%, I could actually work backwards to find the population at the year 2000 or something. So this isn't necessarily the beginning, it just has to be a year that you're pretending is the start. You can work backwards. So there's our equation. Determine the population in the year 2015. Okay, so already we have to kind of understand what value we're subbing in for n. If we're going from 2012, that means 13 should be 1, 14 is 2, and 15 is 3. So we should have an n value of 3. 2015 minus 2012 is 3. So sub that all into the equation, and there's no rearranging, there's no logarithms. You just plug this in your calculator, and you get the answer. The only time we have to use logarithms is when we're trying to solve for an exponent. So as if we have numbers for the exponents, then it's just a calculator question. Throw it in, find the answer. So the answer should be, is that decimal? 182,586.58. So roughly 587 people. So there's that one. If the population continues to grow at this rate, determine the number of years to the nearest year for the population to double. So this is a very common question. Let me slide this up. Now we actually have the p-value. We know what population we're trying to get to. That should be double our a value, so it should be 320,000. This exact same b value, exact same growth rate, and we're trying to solve for n this time. So p is 320,000. We sub it into our equation, and we're trying to solve for n. You can pause the video here and try that on your own first if you like, or you can just listen. I think we've already done plenty of questions like this. Number 1, please don't think that this is all one kind of number, and never, ever, ever multiply these together. That's our grade 9 mistake. All the grade 9s make that mistake. No, this base is stuck with the exponent. It's isolated. This is the odd guy out. He's at the front, so he's the first guy gone. We have to divide by 160,000, which is 2, of course, because it's doubling the population. And then we need to solve this, and we can just use our simple logarithm formula. So log of a base of 1.045 of the value 2 should be equal to n, and you can plug in that into your calculator, and you should get 15.747. So almost all the way to 16. So you will not have doubled after 15 years, so you have to take 16 years. These questions usually we like a nice round answer. It says to the nearest year, not to the nearest month or anything. So you got to round up to 16 years. Even if it was just 15.1, you'd still have to round up to 16 years because you weren't there yet at 15. Okay, example 1, nice and easy. Oh boy, already 17 minutes in. Let's see if I can go nice and quick through this. There's going to be a page we're skipping the middle. Number of fish in a lake is decreasing by 5% each year. So our b value is going to be 0.95. And that's what we have here. Write an equation to represent this. It gives you some variables to use. So n of t is the number of fish after t time. N0 is your initial fish population. You have your b value to some kind of a time. So this isn't a complete equation. Usually you only have 2 variables, usually the guy in the front and the exponent. We don't actually have this value filled in, so this is an incomplete. It's waiting for information, this formula. If there were 2,500 fish in 2012, how many would you expect in 2017? Okay, so what is our n value? 12 to 17 is 5. So 5 years have passed. Please don't count that as 6. Some people count 2012 as number 1, and that's going to give you the wrong answer. Always start with 2013. So n of 5 of 2,500 to 0.95 to the power of 5. And again, this is all a number, so you can just put in your calculator, and you should get the answer. There'll be 1,934 fish, 0.45. Easy, easy. How many years to the nearest tenth would it take for the population to reduce to half its number? And this is almost the exact same question on the last page, so I can just show you the answer here. We're trying to solve for t this time. We don't know what the time is, but we know the initial population is 2,500. We know the final population should be 1,250, should be half that value, and then we just need to solve. So you sub those in, move the coefficient again, that becomes just a half, and then you can switch it into log form. So log with that base of the value of a half should equal your t, and it should end up being 13.5134. If you understood the first question, this should be perfectly fine. If not, you probably want to pause this and try this question on your own. Make sure you can get to this number. But I think we're going to be pretty good with this. And then you write your so therefore sentence. Sorry, I really need to get a better camera. I raised it up higher, but still a little bit fuzzy. Okay, example 3. And let's try this one together. This is our light intensity one. Okay, and I actually have it here. So, the intensity I0 of a light source is reduced to I after passing through d meters of a fog. According to the formula, so we have this formula to work with. You guys are probably used to this in science class. They give you so much information, it's like, what the heck are they talking about? Then they just give you the formula. It's like, oh, I don't even think I need to understand that. That's the way I think about these things anyway, but I'm not a scientist. At what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value? Now we have a problem here. Read that question over for yourself. Pause if you have to. See if you know where to start. The problem we have in this question is we don't know what the starting value is. We don't know what the ending value is. We have our base, which is e. We have some kind of exponent number. We're trying to solve for d. We know that much. We're solving for the exponent in this one. And we know we want it to be 1/4 of its original value, but we don't know what the original value is. And it doesn't actually matter. Whenever you get a question like this, you can actually make the original value anything you want. And I'll show you why. I'll give you 2 kind of really quick examples. Example 1, people usually choose one of 2 numbers. I'll choose the worst one first. The worst one is they say, let's pretend we have, I'll just write it on here. This is our little fake one. Let's pretend I of 0 is 100. So you started with 100 e to the negative 0.12 d. So we're just assuming it was 100. That means we're looking for when it has a value of 25. 1/4 of its original then, right? So the first thing you're going to do is divide by 100, which means you end up with 1/4 over here. Makes sense. We kind of saw that in the original questions. It immediately turns into that kind of number you were looking for. Now, the other most common number people do when they have to pick a number is choose the number 1. And this one works probably better. So they would say, I have 1 e to the negative 0.12. It's just a little bit faster. And that means I'm looking for that 1 when that 1 turns into 1/4. And 1 as a coefficient actually doesn't matter. You could divide by 1. It doesn't matter. It actually just disappears. So it actually kind of jumps right to this answer right away. You can ignore the coefficient, and you're just looking for when it's 1/4. And that's the way you usually want to solve these. And you get quite a few questions like these in this unit. When is it 1/4 of its original? When is it 1/2 of its original? Without telling you what the original value is. Okay, so how do we actually solve this? We have an e here, so it's a little bit funny. We have kind of both ways. We could do it, because it's a little bit complicated up here. So we can't really do it with the logarithmic formula, with the converting forms formula. I'm going to do it with taking the ln of both sides. Often you'll do that with the e, and I actually prefer this method anyway. So take ln of this side, take ln of this side, and I like to leave some room right there because I like to do this all in one step. When you do ln of, I always think this is a little bit confusing because nobody ever writes in, it's ln of all of this in brackets. There kind of is brackets there. Now, whenever the thing being ln'd or logged has an exponent, the exponent can actually come to the front. So I can actually get rid of this, and I can bring it up here. I should have left more space. Let me actually rewrite that. So ln of 1/4 is equal to negative 0.12 d ln of e. Now, the reason we use ln is because ln of e is just 1. That's like a log of base e. So base e, e to the power what becomes itself? Well, that's to the power 1. So this actually disappears. Ln of e disappears. Log of 10 disappears. but this one is actually more common to find for some reason. So now we just have this, and we have to solve for d. So we divide by negative 0.12. D is equal to ln of a quarter all over negative 0.12, which is equal to, and I'm going to actually just take the answer from here, 11.55. Roughly, because we all like that roughly. Try this one on your own. Make sure you've paused it, or make sure you can get the answer at least afterwards, and make sure it makes sense. I'm going to, for the sake of brevity, I'm going to kind of skip the so therefore sentences, but all these pretty much should have a so therefore sentence at the end, because they're all word problems. This whole unit is really. Anything else I want to say about that? I'll make this note right now, because it's going to come up over and over again. In these questions, you're pretty much never going to be asked for an exact answer. You don't actually have to like simplify this into its smallest terms and give the exact answer. Maybe on the diploma you might see that in a multiple choice question, in which case maybe you have to separate this into a subtract ln of 1, subtract ln of 4 or something. But if I was doing this as a written part on our unit test and on the written part on the diploma, I would, well, number one, you can round the answer. So you can give it to me as a decimal and round the answer, but don't do that until the very, very end. Do all of your rearranging first with exact numbers until you get it all into one very simple equation, kind of, and then put it all into your calculator at once. That's kind of the goals we're looking for in this one. Okay. This is the page we're mostly going to skip. I'm just going to talk about it. I think all this stuff down here is actually kind of a waste of time and confusing, more confusing than it's helpful. Half-life and doubling time. So these are very specific uses for the exponential formula. Exponential formula being this. And now we're getting up to the formula that we're going to have on the formula sheet. Do I have my formula sheet here? Yeah. The formula sheet for your diploma has this guy right here, which is y equals a times b to the power, it's hard to see. Where is it? No, that's useless. To the power t over p. So there's actually a division up in the exponent. And this is the first time we're going to see how that's useful. So for half-life and doubling time, this is actually a different way to look at these questions. In these questions, the thing that you're usually solving for is not the b value. The b value now we're fixing. So we're saying that whatever substance we have is going to become half of its original value, or whatever substance we have is going to double. So we're just saying that outright. It's going to double, or it's going to become half of its original value. The b value isn't the interesting part of the question. The interesting part of the question is how long it takes to become half of its original value, or how long it takes to become double its original value. So instead of manipulating the b value, we actually have a new variable for that, and that's this little guy up here. It's the p. The p value stands for, and let's actually write this out. I'm going to write it out nice and big underneath. I'll do it on this sheet. So what each of these stands for, y we know is the final amount. Let's write that equation out. Y equals a b to the t over p. And if you're a person who likes attention to details, the p is usually a capital, the t is usually lowercase, and these other guys are lowercase too. I don't know why. We just do. Y is our final amount. Usually it's a substance we're talking about. Half-life is radioactive substances. Doubling time is very often bacteria, is the most common example of it. So usually it's an amount of a substance. A is the initial amount. So no changes there. B is fixed. either double or half or something else. Sometimes they fix it as something else. Sometimes you might get triple its original value, or how long does it take the car to become worth 90% of what it was originally worth or something. But those are the abnormal cases, and they would have to explain to you what value you're supposed to sub in for those ones. Half-life and double time are the really common ones. Now, T is still, we're used to. T is the amount of time. That is passed. That's like our X value. It's our variable in this one. And you need to pay attention to the units, of course. If you're talking about months, then it has to be months. If it's years, it's years. Now our new one, P. And we kind of talked about this before. This is the amount of time. That's the amount of time that has passed. This is the amount of time it takes to double itself. Or half itself. So P is actually, it's called the period. Maybe I should write that. That's why it's a P. It's the period, it's the amount of time it takes to double itself or half itself. So if I said it doubles every 3 months, so the amount of bacteria in this dish is going to double every 3 months. That's not very realistic. Let's say every 3 hours. Still the same question. So the B would be doubling. T is the amount of hours that has passed, and P would be 3. So every time 3 hours have passed, 1 doubling happens. Because you would sub in 3 for T. It would divide by 3, so you'd end up with a 1, so you would have 1 doubling. When 6 hours has passed, it would be 6 divided by 3, so you'd end up with 2. You'd now have 2 doublings. 9 hours passed would end up as 3, so you'd have 3 doublings. So that's why P works to stand as the period, the amount of time it takes for a doubling to happen. And it's not always bigger than 1. Sometimes it could be even less than 1, but it's usually bigger than 1. So usually you're dividing by some kind of a number. And in fact, it's often even in a whole number, which makes things nice. Yeah, so that's what's going on here. And actually, it is a good way of manipulating the entire graph as well. You could do all the same things with changes in the B value. So you could have had just a different B value and just had T up here to achieve the exact same graph. But it makes more common sense to see it this way when we're talking about doubling or halving. I think I did all this. Don't worry about this formula. We're not using that formula. We're going to stick to this formula up here. And I wouldn't worry about any of this stuff. Let's skip this page. Same thing with this thing. They give you the whole formula, but we don't use this formula at all. We use this guy. So what we did on this page kind of replaces all this stuff, so we can skip this as well. I'm always going to give it to you in terms of these other variables, A, B, T, and P, not these other things. Although you see, sometimes you might see A and A0 and stuff, but that's the abnormality. You want to kind of convert that in your head to this form. A0, if you're not familiar, all you guys have done science, so you probably are familiar. A0 is like, or they actually call it A0 sometimes, is 0 is a subscript. It means the original A value, the initial A value, basically. Okay, let's try example 4. So we have last 3 examples now. Let's see if we can work through them. A patient, here we go. I've got them on here. A patient feeling ill had a sample of bacteria taken from her throat. The sample contained 387 cells. That's our A value. Write them down as you find them. 24 hours later, the sample was recounted, and they found 8,012 cells. So the amount of time passed We use t instead of x because in almost all these examples it's time. The amount of time is 24 hours. So we could call that 1 or we could call that 24, depending on if we want the answer in terms of hours or days. Sometimes you have your pick, but in this case, they want the answer in terms of hours, so you might as well put t down in terms of hours to save yourself a step. And our y value, if we're going to call it that, or you could have called this A0 and this A. I don't really care either way. Both is fine for me. Is 8,012. And we want to find the doubling period, so we're actually going to set our b value to be 2. They've defined this as a doubling period question, so b is just set. But the question is, how long is it taking to double? Find what the doubling period is. So that's our p value to the nearest tenth of an hour. So let's write out our equation. 8,012 is equal to 387, 2 to the power 24 over some unknown p. You could probably estimate this pretty quickly if you want to keep doubling 387 and see how long it takes to get to 8,012. 387, let's say to the power 4. Oh, that's already, it's got scientific notation in my calculator. So that's going to be ugly. Let's just solve this. So, just like our first questions, odd guy out is the coefficient, so first divide by that. Which is a nice question because it says how much bigger is it. So 8,012 divided by 387 is 20.70. Oh, I'm breaking my first rule. Forget that. Sorry. Bad form. Write out the whole number. I could have written 20.0, but it ends up being this horribly long decimal, of course. And 1 decimal point really isn't very good when you're dealing with some logarithms and stuff like that. So we don't like to round 3 different times in a question. So we leave the actual thing and we deal with it later. Okay, what do we do now? Well, we could use our rule of logarithms, or we could do the log or ln of both sides. I like doing ln of both sides, so that's what I'm going to do. Ln of 8,012 over 387 is equal to 24 over p in the front, ln of 2. Okay. I'll do one more line, then I'll jump up. I'm going to divide by ln of 2. So it's ln of 8,012 over 387 all over ln of 2 is equal to 24 over p. Sorry, it's hard to read. I'll write it bigger on the next thing. Next thing we're going to do is flip the whole thing upside down. You can see it 2 different ways. You could either think like, I'm going to flip this side and I'm going to flip this side, and that's allowed because it's like taking both sides to the -1. Or you can think of it like rearranging. P comes up, ln of 2 comes up, and this thing comes down. Actually, why don't we do it that way? So that guy goes up, that guy goes down, that guy goes over, just like we're doing proportions in grade 9. So we would end up with P by itself is equal to ln of 2 times 24 all over ln of 8,012 divided by 387. Annoying to write the whole fraction there, but it is good to do it all. This is just really, really good form. If you turn it into like 20.7 or something like that, it's obviously not a huge deal. You'll probably be very close. You might be 1/10 off, I would guess, in the end, if you were off. But it's not bad. But this is really what I'd like to see, and I think you guys are capable of this. Write it all in 1 and then throw it in your calculator. And the answer should be 5.489. Roughly. And we need to round to the nearest tenth of an hour. So therefore, 5.5 hours, blah, 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 blah. And we add some words there. It takes roughly 5.5 hours for the bacteria to double in this situation, in the person's throat or whatever. Was it a throat? Yeah. So there's that one. Are we on radioactive next? Accident in Chernobyl. This guy. You guys heard of Chernobyl? Scary stuff. Actually, I'm assuming you have heard of Chernobyl. Let's pretend you haven't, though. Chernobyl was a nuclear catastrophe, nuclear meltdown in Russia in the 80s, I believe. I don't know the exact timeline. I think it was the 80s. Could have been earlier. Not really sure. Anyways, a big deal. It looked like it could have been a massive explosion, killed many people. But they got it under control in the end. But I think it was the worst nuclear meltdown in history, as far as I know. It was kind of a big deal. And to this day, it's still a radioactive hot zone. It's they kind of buried the whole thing in this huge concrete dome. But it's still kind of dangerous if you go too near the area. So a wide area around it has been abandoned and it's been reclaimed by nature. And it's actually really cool because there's a whole bunch of species which are starting to thrive there, which haven't been thriving because they leave the area so alone. I think it's wolves. There's like a huge wolf population in the area. It's dangerous to walk around in now. Anyway, fun facts. Actually, I know more fun facts about Chernobyl if you're interested. In April 1986, sorry, I'm already at 42 minutes. Only one more example after this. The nuclear accident at Chernobyl contaminated the atmosphere with quantities of radioactive iodine-131. If the half-life of it is 8.1 days, determine the number of days to the nearest day it took for the radiation to reduce to 2% of its original level. Cool. Do we know what the original level is? No. It doesn't actually say, does it? Nope. If it doesn't say, you can pick any number, and we pretty much always like 1. So we want it to be 2% of its original level. So the Y value we're looking for is 2% of the original. This isn't going down by 2%. This is 2% of the original level. So that's the absolute way of talking, which means we're looking for it to be 0.02. Going down all the way to only 2% of it left. Maybe that's the human safe levels or something. We have our B value is a half-life. And we have the period, this time, is 8.1 days. And we're looking for the time. We don't know what the time is this time. So let's write out that equation. 0.02 equals 1, which doesn't matter. So a half to the power t over 8.1. Actually, a pretty simple equation. Once you get to this part, I trust you guys could probably solve this. So pause the video, try it on your own first, and then I'll just write the last 2 steps. So at the very end of this, you should get t is equal to log of 0.02 all over log of 0.5 or a half times 8.1 or 8.1 on the top. Doesn't matter either way. Should get to that. Logs could be lns as well. Either way is fine. And then you end up with a t-value of 45.715, roughly. So therefore, it took 46 days for the amount of radioactive material in the atmosphere to be 2% of its original. So therefore, blah, 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 everything I just said. Good. Last question. Radioactive isotope. There we go. A radioactive isotope has a half-life of 7 years. Was there a part B to that one? No. But this one has a bunch of parts. I don't have them on this sheet, but we'll do the whole question, then we'll figure it out. Has a half-life of 7 years. So B is a half. The period, it's not time, it's the period, is 7 years, assuming our T is years as well. So the period has to be in the same time calculation as the T value. Determine how much of the isotope must be initially present to decay to 60 grams. So our final value is 60 grams after a time of 14 years. Cool, haven't done a question like this yet. So 60 is equal to some amount of material on a half-life of 14 over 7. That's actually not too bad. You should pause the video and try and solve that. We'll see if our questions are actually write an equivalent formula with. I don't know what that second one is. Your question starts like this. You should pause it, try and solve that on your own first. So the top just becomes 2. You can always simplify that, especially if it's a whole number. That's not going to hurt anything. A half squared is actually a quarter. Again, we weren't solving for an exponent this time, so this is just straight up math. We can do this with the stuff from grade 11 or earlier. So 60 is a quarter of its original value, so its original value is 60 times 4, which is 120, 240. 240. So initially there was 240 grams present. Write a formula with a C value, not C, with a B value of doubling. I don't care about that question. Well, we could talk about it. They talked about it as the C value. So if you wanted to change the B, the growth rate, to doubling, how could you have written this equation? Well, it would have been 60 equals A, and it doubles to the -2. It actually goes backwards. How did they actually get that? I guess what they probably did was they just rewrote the half. I mean, there's like, I can think of at least 3 different ways to get to this answer. But one easy way to see it is you can rewrite the half as 2 to the -1. So it's actually 2 to the -1, and then the 2 exponents will multiply. We had the exponent of 2 times -1 becomes the power of -2. And that'll end up being the exact same one. There's a way to see it as moving backwards in time, but it doesn't make sense with this question anyway. In this particular example, explain how the solution to the problem in A could be found without using any formula at all. Well, you could have reasoned about it. Since you know it has a half-life every 7 years, 14 years should be 2 half-lives. So you're looking for a number divided by 2, some initial value divided by 2 again, equals your answer. And then it's just a fairly simple rearrange. You multiply by 2, multiply by 2. So hopefully that makes some common sense. Sorry this video was 50 minutes long. It's kind of an important lesson, but hopefully it's not too bad. Good luck with the assignment.